The figure below shows 3-point charges that lie along the x-axis. We're going to find the electric field at Q1's position. Which way do you think the field will point? So this problem involves the principle of superposition. And what that means is that more than one charge can contribute a field at the position of Q1. We have a negative charge on the right, and there's a negative charge on the left. Both of these will make a contribution to the total electric field. When we're evaluating the field, we don't need to know what charge is at that location. We can actually just remove it from the problem for a minute so that we can focus on the contributions from Q2 and Q3. This is because a charge can't exert a field on its own location. Charges can only create fields from a distance. So some of the things we'll need to know to solve this will be, we need to know how many coulombs are at these locations. And we'll also need to know the distances from the charges to the point where we're evaluating the field. This distance will be called R2, and this distance can be R3. We see that R2 is 0.2 meters, and R3 is 0.15 meters. We're also going to need to know K, which is Coulomb's constant. 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. All right, so before we even do the calculations that are required, we could take a guess at which way we think the total field will point. So at this point, which I'll call P, how strong will be the contribution from the right side, and then how strong will be the contribution from the left side? It's something to consider. Now, Q3 has a larger size than Q2. And the larger size the charge is, the stronger the field contribution will be. We also know, though, that the smaller the distance is between these two, the larger the electric field contribution will be as well. So those two things allow me to know that the field contribution from the right charge is going to be greater than the field contribution from the left charge. And the mathematics will reveal that this is the case. I'm going to call this E3, and the one on the left can be E2. They need to be added together as vectors. This is the principle of superposition, that both charges can contribute to the total field. One way to write this mathematically is E total equals E2 plus E3. Okay, so at this point we want to replace the E's with their formulas. And you also have a lot of options about which way you want to approach solving this mathematically. So one option, which I think is the easiest option here for getting started, is to just use the size of the charge in your formula. So you could use an absolute value. And then assign the direction based on what you see in the picture. So E2, we know, according to the picture, has to point to the left. And so since it points to the left, I can decide to put in a negative I hat as my direction. Positive I hat would be to the right, negative I hat would be to the left. When I do it this way, I don't use the sign of the charge to determine what the direction of the field is. I just look at the picture and know that it has to be a negative. So see, I don't want a negative in my Q in that case, because a negative times a negative would flip it to positive, which I don't want. And now I do the same thing with my Q3. KQ3 over R3 squared. I look at the picture, I see that the field contribution should be to the right. So we make this one a positive I hat. Now, how did I know that E3 pulls to the right? Because you have to imagine what a positive test charge would do if it was located here. Positives are attracted to negatives, and that's why the field pulls to the right, and our Q2 would pull to the left. So this simplifies the mathematics quite a bit. Now we just have to plug in the numbers. I'll round our Coulomb's constant to 9e to the 9, that's common. And now we'll just plug in the size of the charge. Divide by our radius squared. And we'll keep our negative I hat. And we'll have that. So let's calculate and see how large each of these magnitudes are. All right, we get 900,000 here. As we suspected, the contribution from Q3 ended up being much larger than the contribution from Q2. Okay, and as we can see, our E2 here is smaller than our E3. And that should make sense according to the picture that we drew. We want to now add them together to get E total. It ends up being 1,900,000 newtons per coulomb. If we wish, we can redraw our diagram and show that those two vectors add together to just a single field pointing to the right. What that means is if there is a positive charge here, it's going to feel pulled toward Q3. Okay. So which direction does the field point at Q1? It points to the right. Now here's another question though. Which direction do you think the force on Q1 will point? Remember that at the location of Q1 is a charge, a positive charge, plus 6 times 10 to the minus 6 coulombs. So that positive charge is going to feel pulled to the right as well. If that charge happened to be negative, the opposite would happen. It would feel pulled to the left because the negative would be more repelled by Q3 than it is by Q2. Okay, so before I end this video, I want to show one more way of calculating this same problem. And it's a little bit more advanced. All right, so the other way of approaching this is to use the full formulas for E here, which would be KQ2 over R2 squared R2 hat plus KQ3 over R3 squared R3 hat. And you have to think back to what the definition of an R hat is. So R hat points from a charge toward the point where you're evaluating the field. So that would be R2 hat. And this is R3 hat. Notice an important fact here, that R2 hat is the positive x direction, and R3 hat is the negative x direction. What we could do next is do a substitution, where we take this and plug it in here, and take this and plug it in here. In doing so, now we don't have to use an absolute value in our calculations for the charge. We can just let the charge be what it is, and the mathematics will work itself out. Remember that we want our field due to Q2 to point to the left, and we want our field due to Q3 to point to the right. Let's see if the mathematical approach here works itself out so that that's the case. you'll see that the signs do work themselves out so that they have the correct directions in the end. E2 points to the left and E3 points to the right. So it's good. That's a little more advanced way of approaching it, but it is a useful way of doing it, especially when you get into two-dimensional problems.